Okay, sir. We can start the session. I think the climate is getting worse, so we can start now. Can you hear me, sir?
Yes, yes, I can hear
Okay,
you.
sir.
Yeah,
Okay.
thank you.
Dear participants, we have reached the third session in our day 4 FDP on mathematical foundations for machine learning. In the third session, we are discussing about the topic mathematical models for machine learning. And our resource person to handle this topic is Dr. Ragesh NK. About our resource person, Dr. Ragesh NK is an established technocrat working on application of advanced technologies to real-world products. He has over 20 years of experience in industry, focusing in automotive domain. He has industrial experience in the area of signal processing, AI and ML. He is currently heading the cybersecurity practice in automotive business unit, Tata Elxsi Technopark, Trivandrum, Kerala. About his academics, Dr. Ragesh received diploma in computer engineering with state rank from the Board of Technical Education, Kerala. He did his BTech in computer engineering from Madras University and MTech in digital image computing from University of Kerala. He received PhD in advanced driver assistance systems from Bharatiyar University. His research interest includes digital signal processing, computer graphics, and he has published many research papers in well reputed journals. We are very much privileged to have Dr. Rakesh NK as our resource person today. On behalf of Sri Buddha College of Engineering, I welcome Dr. Rakesh NK to handle the session today. Welcome you, sir.
Thank you. Thank you. Hope my screen is visible and I'm audible.
Yes, sir.
Okay. Okay, thank you. Then we'll start. Uh, yeah, so the topic here is mathematical models for machine learning. And I'm very sure that, okay, you already had gone through different sessions for machine learning with details on how the machine learning is happening for different cases, what kind of machine learning algorithms we have, how to implement a algorithm, how to compare them, how to compare the performance. So on these, all of these aspects, you might have already heard different sessions, and all those sessions may be definitely academically focused. So you'll get more technical details there. So here I find that I'm the only person from an industry background. So I'm not taking the risk to go in depth into the technical details of the algorithms, but rather I would like to cover it in a different perspective. How the mathematical models are used for machine learning in an industry perspective. So that's what I thought to share with you. So I'll not be going in detail into different algorithms, but rather I'll be giving you an overview how industry is utilizing these algorithms and how practical problems are getting solved utilizing these machine learning. I hope that will be fine. So here, okay, this slide shows what I am addressing and try to cover in this session. So I'll give you a very brief understanding of learning and machine learning. You might have already gone through it, but please bear with me to hear it in a different, slightly different perspective. Uh, I don't know. Maybe other sessions also cover the same perspective. Then next point I would include is mathematical modeling. How mathematical models, what kind of mathematical models are used in machine learning. So I'll take some example and give you some overview of how the modeling concept is being used in industry perspective for the machine learning operations. Then, since I'm coming from an automotive background, automotive industry background, all my examples and the cases or use cases, whatever I'll refer, will be from that industry background. So I'll give you some examples of how machine learning is used in industry perspective and what my company, that is Tata Elxsi, is doing on that. So I'll give you an overview of this aspect. Then we will also discuss or see some videos on some samples that we are working on to get you a better understanding. So I did not prepare so many slides, but I would like to expect, I would expect to have an interactive discussion where I am open to answer your questions as we discuss. Okay. So let's start with this machine learning or the learning concept. So what is basically learning? When you think on yourself, okay, how do you learn? How do we learn? So learning is a kind of representing whatever we observe or we perceive in a form which we can reuse or recollect. So that's the process of learning. So how do we learn? So we have many what's the researches happened to understand how we learn. Uh, Research is still in progress as we don't know exactly whether what we say is correct or not, or what we understand is correct or not. But generally, what we understand is that okay, we learn things in our brain as something like a network. So we learn things in the form of a network, an interconnected network where the weights of this network or the strength of this bonding uh, is the factor or is the determining factor how a pattern is captured into it. And everything what we perceive will be mapped to a kind of a pattern which we can regenerate or recollect. So this is whenever we remember things, we will actually touch on edge of this pattern, and this whole pattern activates. So we will get a feeling of what we perceived. So this is what is basically learning. That is what we understand, and we utilize this same concept to what say extend the same idea to the machine learning also, that we all know the artificial neural networks and all. So so basically, okay, one factor we need to think here is every individual perceives things in a different way. So whatever we learn is our own way, our own way in the sense, okay, we will learn things in a pattern which is unique to us. So if two people are learning or seeing same scene, both of them will perceive it differently. So for example, okay, if I sense the color red, so the red color in my pattern will be different from a red color in somebody else's brain, but both call it red. So that's why there is no confusion. Okay, both call it red. So there is no confusion in that, but the actual learning what happened is unique to every individual. So we can extend the same idea to see that okay, we are actually living in a virtual world. That is, we are living in a world which we created by what to say, modeling from the sensor, the different sensory organs that we have. So we are perceiving through different sensory organs. We accumulate all those learnings or all those patterns that we perceive from these different sensory organs, and then we model, we create a kind of a model within our brain to understand the world around us. So actually, we are living on a virtual world. The world is unique to me, but it may not be the same way captured with somebody else. But there are some generic terminologies we use about this. That is how we learn from our childhood. So this learning or this generic jargon that we learn from our childhood helps us to communicate this in a agreed way, mutually agreed way with our what to say, other human beings. So this is how we actually perceive the things. So we can easily understand that we are also actually modeling whatever we perceive. So the same concept is being extended to a machine also. So whatever a machine senses through its different sensors, we call it sensors, it will create a kind of a model out of these inputs that we get through its sensors, and then create that model as a reference to whenever we need to what say derive some decisions out of these inputs or this world or the interaction between different elements of this world. So what I want to highlight here is, okay, whenever there is a learning, the fundamental thing what we need to have is a model. So any model should definitely have some mathematical what to say composition. So without a mathematical composition, no model will be complete. So mathematical modeling is the fundamental thing for human beings learning as well as for a machine learning. So we will establish that first, and then we need to think all the learning or machine learning in that perspective. The another thing in computer or in a machine learning is how we visualize it. Because okay, as a human being, we learn things how to communicate. Okay, if I think a red, I know to represent or to communicate it as a red, that pattern. And others also learn the same similar feeling and similar patterns, and they also know what I mean by red. But how the machines can communicate? So for machines to communicate each other as well as machine to communicate with a human being or an operator, there should be a kind of a visualization. So the visualization itself is kind of a representation of the model. So for a machine learning, the mathematical model and its visualization is very important. Now let us see how the machine learns, or how the artificial intelligence is what's it captured. So this is a simplified diagram of a machine learning and artificial of the machine learning process and an artificial intelligence system. So okay, on the machine learning side, what we can see that okay, we will first define a problem, then we will identify some sample cases which represents that the what's the inputs or the different scenarios. Then we will also evaluate those sample cases and understand how these sample cases can be represented in an efficient way by implementing or by utilizing some features which is extracted from the behavior of these inputs or the sample cases. Then what we'll do is, okay, we'll generate a mathematical model out of these features. So this mathematical model will actually be a representation of the common, what's a common behavior of these features, and it will also help us to take some decisions regarding what's a, these sample use cases or a similar input when we get in a real time. So we will create a mathematical model. So by f of x, I mentioned it's a representative mathematical model. Okay, so a machine creates its perception into a mathematical model from the defined problem by taking or by observing and analyzing the sample cases it have, and representing it in efficiently utilizing features and generating a model. Then while doing the actual intelligence, so while doing the decision making using the intelligence, the machine actually does the similar operations to extract the features, because it knows how to represent a unique set of samples. So the same method is used to extract some features from a real life sample, and then these extracted features or representative data will be fed into the model to generate the output. Then this output is used to take the decision. The decision may be anything, maybe what is a binary decision to say this particular sample belongs to the, group A or group B, or it belongs to group A or not group A. So the decision may be different depending upon the actual scenarios that we need to address. But however, the decision is done based on the output of applying these features into the mathematical model. Okay. I hope this is clear, and I'm moving to next page. So I would like to take an example here from an automotive industry perspective to see how a typical AI artificial intelligence application is done. I'll play a video here. Let me know if you are not hearing the sound, but sound is not a big deal because it's only a background score. So I'll play this video. Just let us go through this first, and then I'll come back to some explanation. This is an auto parking solution developed by ATAL-FDP, and the video what we captured is while experimenting it within our premises. Okay. So basically, auto parking helps us to, or the vehicle will do the parking automatically, so that we can keep the vehicle at a designated spot, and the vehicle will itself go to the parking slot. Okay. So so this is a demonstration of how auto parking is implemented in a Tata Tiago car. So this is, you can see that it automatically parks or finds its parking space, and it automatically moves to the parking lot from the drop point. So and also whenever the everything is initiated through a mobile application, and whenever it is asked to come out of its parking lot, it comes back to the drop point. Similarly, whenever there is an obstacle on the path, it actually identifies that, and then stops to avoid any collision. And then once the path is clear, it continues the maneuver. So this is what we saw in that demonstration. Let us observe that problem. Okay, how this is being executed. So here, what I'm showing here on screen gives a kind of a representation of what is being happened while doing this operation. So in bottom line, you can see that okay, there is a drop point and there is a uh, uh, identified uh, empty spot. Sorry. So the vehicle is starting from the automatically the start. What we mentioned here is the drop point. So from there, vehicle start itself and then moves to the designated point, designated parking lot, and this is the stop point for that vehicle for that maneuvering. And it actually in a practical scenario, this the situation will be more complex, and there will be a practical parking ground where there may be multiple parking free slots available, and most of the slots will be occupied. So it also has to identify the best, the most preferred parking lot, parking spot by seeing the easiest access considerations. Then it should start moving by observing the path and finally reaching the stop point. So whenever it has to come back, it has to continue the same process and come back to the drop point. So okay, the whole operation starts from logging the start. So start logging means okay, yeah, I'm ready to go. Then okay, it has to plan the path. So it has to identify where should I reach, and then how should I reach there by considering the known obstacles on the way. So for that, it has to take different inputs. Actually, it will take satellite signals to generate, to understand the coordination of its positioning coordination. And then it also gets a map data where it places this its position into the map to understand the real position of that particular vehicle in the map. It also get live traffic data. Live traffic data means okay, it may be from a fixed traffic data which is available for the traffic data databases, which is this is applicable in a practical case, but in the demonstration this was not used as an input because it is demonstrated in a constrained environment. But whenever there is an actual maneuver to happen, we have to get the traffic data from the traffic databases. So all these things will be combined, and we will create an optimal route from start to stop. So that is the path planning operation. So here, whatever I what is that I what's drawn in blue color is the input, and these whatever drawn in red border are the models which is created uh, out of these inputs. Then next step will be continuing the maneuvering by detecting any object or obstacles and its maneuver. So if an object is moving towards the vehicle, it has to stop. If an object is found moving out, outside the path of the vehicle, it can ignore that object. So the objects needs to be detected and tracked to understand where these objects are moving, or are they static objects which do not move, so that okay, the vehicle has to move around it. So for doing this object detection and tracking, different sensors are used like camera, radar, and lidar. So whatever we see in our demo, we used low range radar as well as a camera to sense objects crossing the path. So from these sensors, what it will do is okay, it will okay, if it is camera, it will directly be applied with an object classifier model, and then once object is classified, we will create object behavior model to understand how that object can potentially behave in an environment. Similarly, from radar and lidar, the signal has to be first beamformed to generate the pattern or generate a 2D or 3D representation, and then the classifier model it is being applied to the classifier model to identify the object, and then again it will go to the object behavior model to predict the behavior of that particular object which is detected by these different sensors. So once each of these individual sensors detect these objects and behave and model its behavior, it will be given to the sensor fusion model, where these models will be compared and what to say, blended or merged together to form a more robust model. So lidar may be detecting in what to say, clear sky conditions, where a radar can detect in kind of a rash environments or a night time. So some sensors will be more efficient in some environmental conditions, whereas others will be effective in some other conditions. So all these needs to be considered while what to say, assigning a kind of a probability or assigning a kind of a weightage to inputs from these different sensors, to make to fuse those different sensors sensor inputs to generate the object model or the fused sensor fusion model. So from the sensor fused sensors model, we again need to create an object behavior model, because it is more robust now, and it is having different kind of inputs to make it more accurate. Then once the object behavior model is prepared, we also need to generate a multi-object path model, where there will be multiple objects, and each object may be behaving in a different way. So all these needs to be captured to make sure that again none of these objects are crossing the path of this car and obstructing it. So this is done as part of the object detection and tracking. So once we find out that there is no what to say, blocking element or objects which are blocking the path of this car, it will continue its maneuver. But if it find that okay, some objects is blocking the path, or there is a chance that an object can come in front of the vehicle so that there could be a collision later, in that case it will go to a real-time path adaptation stage. So the real-time path adaptation stage is also a kind of a complex model. It also utilizes a complex model, where you can see that it will take multiple inputs. Okay, it will take the same GPS input and traffic data, just like the path planning, and it also takes the environment data, vehicle behavior data, and event data. So the environment data actually explains or gives inputs on the environment where the particular vehicle is currently in. Vehicle behavior data gives how the vehicle responds to different interactions or inputs, and what kind of maneuvering is possible and how to control it. Event data actually gives more details on any specific events that is currently happened in the environment, which is of importance to what's controlling the maneuvering of this vehicle. So from environment data, it will create an environment model. From vehicle behavior data, it will create a vehicle model. Then from event data, it will create an event severity model. So if an event is severe to this particular operation, that is maneuvering from the drop point to the parking lot, it needs to be counted. So by counting all these things, it will create a vehicle behavior model, which will explain how the vehicle should interact or should behave or should respond to the environment where it is. Then it combined with the positioning data, there will be a optimal routing and navigation system or a model is generated, and accordingly the vehicle is being controlled and maneuvered. So the real-time path adaptation is, once real-time path adaptation is done, then again, okay, it is moved. Okay, it moved to the next stage, and again, okay, at each of these maneuvering at periodic intervals, it will check whether it reached the destination. If it reached the destination, it has to stop moving, and the stop needs to be locked. If it did not reach the destination, the whole process of path planning, object detection and tracking, and real-time path adaptation needs to be repeated until we reach the destination. So this much what's a mathematical modeling and kind of complex processing is being happened in background when we see a vehicle is moving from point A to point B automatically. Okay. So I hope this will give you an idea how different kind of models are being used in a practical problem. So whenever we say about models in machine learning, we will be only discussing the classifier models or object detection models. But above that, there are so much of computation happening in background whenever we actually implement the same in a practical scenario. Any questions here? I assume no questions, so I'm moving to the next slide. Okay. So we have seen different models there. So I'll once again go back to the previous slide and say that, okay, whatever the blue, what is a bounding boxes, all are inputs, and whatever written on the red bounding boxes are models. Some kind of representation of this input data, maybe a raw representation or a processed representation. So all of them can be considered as a model. Now, okay, coming to two type of model. Okay, one thing is the machine learning models that we typically use in classification operation. Okay, okay, how the we will call it learning models in machine learning. So there are two categories mainly: supervised learning as well as unsupervised learning. And under supervised, there are regression models which are generating continuous output, whereas classification models generate discrete decisions or discrete outputs. There are also deep learning models which are kind of classification or regression, but the importance here is, okay, it is a kind of a self-adapted model, or it automatically choose the best feature to proceed with the learning operation. So it's being extensively used now. Its computational requirements are slightly higher than the typical classification or feature classifier models, but its accuracy and the potential of using it in different practical applications are much higher. So under each of these models, there are different models you can see. And under regression, we have linear regression, which uses a kind of a polynomial fitting. Then decision trees, where we step through or process through different nodes to take intermittent decisions and finally reach the final decision at the leaf node. Then random forest is a kind of a ensemble learning, and it uses bootstrap kind of processing for progressive learning. Then we use neural network. So we will say artificial neural network, but we will simply say neural network in general ML sense. So it's having multiple layers. There are input layer and output layer, and multiple hidden layers, which takes decisions as something similar to how human learns. Okay, when we comes to classification, we have logistic regression again doing the classification operation. Then we have support vector machines, we have naive-Bayes decision models, and we have decision trees. Again, random forest and neural network are there. Then coming to unsupervised learning, there are clustering as well as dimensionality reduction models. Clustering models, there are multiple different categories into that: k-means clustering, hierarchical clustering, mean shift clustering, and density based clustering. So all these are kind of a grouping of data. So there is no guidance on which belongs to which group here. So the system automatically groups the data into different groups. And then whenever a real input is coming, it finds the best match among this group for that particular element by kind of measuring the distance between mean, or whatever way we can measure the similarity between the patterns or features generated out of a real data to that of these different clusters or groups that we generated out from the input data. So whereas supervised learning, we clearly say these are the group A, these are the elements of different groups, and whenever a new data is coming, it is easy to understand the pattern which is matching the best way. So supervised always helps us initially or as part of learning to understand which belongs to which group, whereas unsupervised will not provide any such inputs, but the system automatically groups the data based on the actual pattern or actual feature output generated from the inputs. Then, as part of unsupervised learning, there is a dimensionality reduction where we actually, what to say, eliminate the dimension of the features or reduce the dimension of the features to finally reach the acceptable number of clusters. Okay, so PCA, principal component analysis, is also a kind of machine learning model used in dimensionality reduction. So all these models are machine learning specific models. But along with this, we also mentioned about other models that is being used in model-based design and development. So typically, we can categorize them into environment model, component model, and visualization models. So I categorize the mathematical model for simulation. So simulation is the kind of representing a real thing in a virtual way. So for doing that, we have to model the environment, we have to model the component, and we also have to have a way of visualizing the interaction of this component into the model. So for modeling the environment, we actually have to capture all these parameters of the environment. Uh, if time permits, I can show you a kind of tool which we use internally to do that. Okay, once we complete the other slides and discussion, we can cover that. So it actually captures different parameters of the environment and creates a model out of it. On the component model, we have to actually model how the components are what's a constituted with all its interfaces to the environment. So what kind of interface it is having to the environment, and how the particular component is separated from the environment. Then next one, what we need to do is a behavior model, where we need to predict or we need to capture how the particular component will interact with different triggers from the environment, or different changes what is happening in the environment. For example, okay, if a car is moving and it is finding an object in front of it, how it should behave in that sense, whether it will continue moving and hit the particular object, or it will stop, or it will slightly steer right or left according to the condition and move around that object. So what way it will behave when it finds a particular event, so it encounters a particular event in the environment. Then the another thing that we need to model is the control models. So how the vehicle needs to be, how the model, the component needs to be controlled in the environment, and what kind of inputs can be externally provided to it. Other than its interfaces, what kind of inputs will be required to control the maneuvering of the particular, or maneuvering, or we can say the existence of the particular component in that environment. So all this comes under the component models. Then in the visualization model, it's a kind of a graphical representation in 3D or 4D space. Okay, in this representation itself, we need to represent or visualize the environment. We need to visualize the component, that is the particular object of interest, and also we need to visualize the interactions, how it is getting interacted, how the model is or the component model is interacting with the environment. So how to visualize that? So all these things we need to model, and within the environment itself, okay, we need to model the visualize the interactive objects as well as non-interactive objects within the environment. Similarly, the component, we need to visualize the fixed components as well as moving components. So whenever a component is moving in an environment, it makes things more complex, the visualization more complex. And there will be a number of such components in an environment where these components interact together and coexist in the environment. So all these interactions, all these communications, all these behaviors needs to be visualized. So all these are requiring some kind of mathematical modeling. It's not just the machine learning models that we always say. Okay, so with this, I think I covered the mathematical models in AML. Now I will pause here for any questions. Any questions or comments you have, please let me know. Am I going in a faster pace, or is this okay to proceed like this? Or you have some specific points on something I discussed here? No questions? No comments? I hope I'm audible. Hello?
Rajesh sir, one question
Yes.
in the chat. What algorithms are used for path planning Dijestra's algorithm?
Yeah, this Dijkstra's algorithm and all we have learned on how to plan in a graph. Okay. So there are different algorithms like that, and there are some customizations also applicable. I can give you some kind of inputs on that later, but I did not prepare a kind of detailed technical discussion as going into each of these algorithms and how that algorithm performs.
Okay, sir. Okay, sir.
So shall I continue now?
Yes, yes, yes.
Okay. Yeah, so I have discussed about learning and the mathematical models used, and I took an example from automotive industry, that's an auto parking, and also mentioned what kind of models are being used internally to implement that particular scenario. Similarly, in automotive industry, the automotive industry is one industry where the machine learning is of high importance and it is extensively being used. So, machine learning is not only for this kind of vehicle maneuvering, but it actually covers some other aspects also. So, I listed out some of the applications of machine learning under three categories here. The first thing, it's autonomous driving. Okay, autonomous driving is the first thing we all will think when we say artificial intelligence to a vehicle. So it can, or it will capture, or it will learn how to drive itself. So that's the first thing. But even within the autonomous driving, we have different sub categories or different phases or different stages of implementing this. The first thing what we can see is it's a kind of a driver assistance where the vehicle will not take any decision as such, but rather it will understand or it will perceive the events within the environment and indicate the same to the driver, so that driver can take the decision to avoid any collision. So whatever the sensor fusion, the sensor input, object classification, object detection, all these things will come as part of this driver assistance system. The next thing is kind of a navigation and augmented reality. So augmented reality is a kind of a little bit more complex. So it has to actually understand, uh, uh, it actually needs to take a high definition 3D map as an input, which actually captures every single element in the environment into the map, by what to say, by naming each buildings, each roads, each intersections, and each objects on roadside, as well as what to say, in the environment. So everything needs to be captured in a high definition map. We call it HD map. And the vehicle's GPS location is also needs to be captured. Then we merge this vehicle's position and direction and alignment to with into that map. And then we actually need to what to say, visualize how the scene or the map will be visualized or seen from the driver's position. So we need to map these coordinates to a driver's visible what to say angle, and also needs to identify different objects within the HD map within that viewing angle and name them. So what we will observe from a vehicle perspective is, driver will see each of the buildings or the objects he sees in front of him marked virtually with its names or important notifications needs to be, or important messages regarding that object. So it is called augmented reality. So we have a real thing here, and we are augmenting it with some additional data. So to visualize this, we need to have a windshield display where these additional notes or messages will be displayed on the windshield itself, uh, from what's by understanding how the driver sees it. So computing the position or the intersection of the viewing direction and the windshield and the actual object, it will place the messages in the right place of the windshield. It will be a transparent display. Then the driver will see that, okay, every object that he see in front of him will be named and will be tagged with additional what's a sticky notes on it. So this is a kind of augmented reality that we are working on now for the new generation vehicles. So it involves so much of computation in background to implement something like that. And also the display technology also used here is also different. So it uses a kind of a display called head-up display, where the display will be done on the windshield, but when we see it, we will feel that, okay, the display, the actual tag is put on the actual object. So it will automatically create the distance feel while we display something on the windshield. So if I'm seeing a building 100 meter far from my position in a vehicle, I will find a tag is attached to that building at 100 meter away while seeing through my windshield. The actual display is happening at windshield, but it actually generates a virtual feel of distance, so that the driver don't need to focus on the windshield to find what is written there. He can focus on the objects that he see in his front, and there itself he will see the notes. So the technology used there is much complex, and it is getting evolved now, but this is coming into reality now. So we can see in the fairs like CES and all. In the automotive session, we can see how the augmented reality displays are getting into the vehicles, and how the experience is getting improved based on that. Then another way of autonomous driving is constrained autonomous driving. It is similar to what we discussed now, auto parking. So we are not driving anywhere, but we are driving in a constrained environment. We know where to drop the vehicle, and where it could be parked. So all these things will be pre-identified things, or it creates a constrained environment by defining where to start and where to stop. So similarly, auto braking is another constrained environment condition, because it identifies an object and it calculates the distance, and it actually identifies how much brake pressure needs to be put to stop the vehicle before hitting the object. Then highway assist is another feature where the vehicle will follow the vehicle will follow a vehicle in front of it. So it will always keep a safe distance automatically with the vehicle in front of it, and moves whenever that vehicle moves, or stops whenever that vehicle stops. So the driver can sit idle. So this is much suitable in highway driving, as well as driving in traffic jams. So all these are constrained autonomous drivings. Then next stage is fully autonomous. It is much more complex than the constrained and autonomous driving conditions. So this actually ends to driverless vehicles. We all know that Google is experimenting with its driverless vehicle. So it actually is equipped with a whole set of sensors, and all these sensors will provide different kind of inputs, and all these inputs will be sent to a cloud server, where the cloud server will do the analysis and help the vehicle to take decisions. And in some constrained environment, the vehicle can do the decision or take the decision itself, but it requires a highly complex or highly computationally computationally powerful computers within the vehicle. So there are different conditions like that, how a fully autonomous driverless vehicle can function. So it's a kind of a future of how these autonomous driving or the artificial intelligence applied to a vehicle is going to. Then all these are implementation. Now again, to do the implementation and validation of these features, we need to also have a simulation. So we need to also apply some mathematical model to simulate the environment and the vehicles, and identify whether our designed algorithm will work properly to handle different scenarios or dynamic scenarios that can happen in the environment. So simulation is also utilizing much more artificial, as well as mathematical artificial intelligence, as well as the mathematical models to do the actual mimicking the environment where the object is getting placed. So all these coming under autonomous driving. So similarly, for the passenger experience also, we have a requirement of applying the mathematical modeling as well as AML. So first thing what we can see is a seamless experience. So a passenger would like to treat the vehicle as an extension to his home. So whatever media he was accessing at home, he need to continue from the vehicle side. So this may not be applicable to the driver, but for the passengers it will be applicable. So if I was reading the newspaper at home and I would like to continue reading the newspaper from my car, so I need to capture what I was doing, or I need to the system here is much more complex. So to implement such a seamless experience, a model needs to be created for the particular passenger, how he interacts with the world, what kind of activities he does, by at what time what he does, then what is his preferences. So all these things needs to be captured and modeled, so that the same experience or environment can be provided anywhere in the sense, it could be in the vehicle or it could be in the office. So once the person's behavior and his or her interactions are modeled, as the environment changes, the model can define what will be the interaction, what will be the predicted expectation or the expectation from the passenger in that condition. So accordingly, it can provide the data. So that's the seamless experience, what we discussed now. It's a buzzword coming into the automotive industry also now. The next thing is the personalization. So personalization is a kind of a part of seamless experience, but it is more focused on the person. So we need to understand the person by understanding his behavior, what kind of interaction he's having in social media, what kind of activities he's doing, what is his routine, what is his typical way of handling things. Then understanding all these things, the vehicle will prompt the passenger with suggestions on right time. For example, okay, if I have a habit of taking a coffee every morning, and somehow I'm missed to take coffee because of some other aspects, and I'm going to office. So on the way, if there is a coffee shop, the vehicle will tell me that, okay, yeah, you missed your coffee and you can have your coffee here, or shall I order a coffee for you so that you can collect it when we pass through that place. So these kind of suggestions will be given by the vehicle instead of the person asking the vehicle to do something. So now the interaction part we see is, okay, people can talk to vehicle to do things, but the next generation will be vehicle will be talking back to us or suggesting us what we should do. So the ideal experience is, okay, if we think something, the vehicle, before we speak it out, the vehicle will ask, do you want this? So this kind of experience we are focusing for the personalization now. Okay. Then next thing is in-vehicle entertainment. So as the electric vehicles are coming more, the Tesla is an example here in providing good in-vehicle entertainment. So actually, Tesla allows the passenger to use its steering wheel to play a video game while the car is being charged. So for example, to charge the vehicle, we need to spend at least half an hour to 1 hour. So during this time, the person is sitting idle, or the car is sitting idle. So at this time, the passenger can use the vehicle steering wheel to play a computer game. Okay. So everything is software controlled now. So vehicle steering wheel can be used as a game steering wheel also. So it allows to do that. So that kind of new ideas are coming into in-vehicle entertainment. So whenever there is a time, the car helps to entertain the passengers. So intelligence is needed to do that, and different kind of models are needs to be implemented to do this. And what's a different kind of behavior and personalization also needs to be included into this. As a third area where AML is used in automotive industry is intelligent traffic planning. So intelligent traffic planning utilizes the real-time traffic data captured through different vehicles on road. So for example, Google Map helps you identify a different path or different road when there is a traffic or congestion in one road. So it actually captures the data from every mobiles which is using its Google Map, or it's at least it's GPS activated. So Google is collecting all these GPS information from all these mobiles and see how the vehicle is getting moved. If a vehicle is moving slow in some place, it will identify that that road is having some traffic, heavy traffic, and it's a slow moving traffic. So it will inform this same to other users, and most probably automatically takes some kind of diversion to enable other vehicles to reach the destination in a faster way. So this is a real-time traffic data which is getting generated by every vehicles, every mobile phones. So all these will be collected by a cloud system, analyzed and used to help passengers to move easily across the roads. So that is kind of application of real-time traffic data. So same data is used to predict congestions and rerouting that I already mentioned. The next thing is rerouting to meet customer interest or predicted behavior. For example, okay, if I want to, okay, just the same example, okay, if I miss my coffee, I want to take a coffee, the vehicle will ask me, do you want to have a coffee? So if I am saying that, okay, yeah, I need a coffee, or if I'm confirming that I need a coffee, it will automatically reroute to a path where a coffee shop is available. Okay, it may be a different path, but other than usual, but because the vehicle expects that the passenger needs a coffee, it does a kind of a predicted behavior, and it confirms with the driver or passenger and reroutes to meet the customer expectations. So these are some areas where the artificial intelligence and machine learnings are getting implemented or getting what to say into the automotive industry. So to enable these kind of implementations, we are actually progressing with connectivity for the vehicles. So every vehicle is getting connected now. So every vehicle will be having an internet access, and through internet access, it can access to any such similar devices, any similar roadside units, or any such any other vehicles, or any kind of what to say connected IoT devices or sensors across the world. So that connectivity is getting into every vehicle now. Next thing is the social media. So the advances in social media helps to predict the human behavior in a better way. So that data is also being utilized by these techno giants to predict the behavior of a person. So connected vehicles is actually extension to the connectivity. So every vehicle is getting connected now, and the data you generated by the connected nodes or every vehicle. So every vehicle is providing, capturing the data from its environment, and it's also uploading the same to the cloud systems. So the cloud systems can utilize these data to learn some patterns and some behaviors, and help drivers or passengers to for some purpose. Okay, maybe to ease their driving experience, or maybe to ease their personal experience. So for multiple purpose, this is being used. Then okay, the advances in AML and DL, deep learning. So all these helps the advances in the sense, okay, earlier, okay, we know that we need a high performance computer to perform machine learning operations and deep learning, implement deep learning algorithms. But now these algorithms are getting more into an embedded friendly way, where a kind of a device which can, a portable device which can fit into the vehicle, can also do this kind of complex operations. With the help of additional connectivity, it can have a minimal implementation at offline, and it can verify the same parallelly with an offline connectivity. So this is the kind of advances happening in AML, which is accelerating the application of it in the automotive industry. Okay, then high performance computing platforms are also coming into the embedded space now. So the NVIDIA is now proceeding with different high performance computing platforms for specifically for embedded systems. So that also helps us implementing more complex algorithms within the vehicle. So this is how things are happening in automotive industry. By utilizing these kind of different AI/ML techniques for enhancing the experience, the driving and traveling experience in general. Any questions here? No questions? Okay.
Dear participant, any questions? Dear participant.
Okay, the whole purpose of this session is to communicate some trends in what's a AML in an automotive perspective or in an industry perspective. So I hope you are capturing it, you are understanding it, and if you feel some difficulties in getting these points what I explained, please let me know. If I need to go in a slower pace, I can do that, or if I need to focus on some specific aspects, I can do that. Uh, but okay, I'm not going deliberately. I'm not going in deep to the specific algorithms, definitely, because that will take a lot of time. So give me your suggestions. Okay, if you are okay with the pace we are moving, I'm fine. But if you have any suggestions, also let me know. Okay, I think everybody is happy with what we hear. I hope you are listening. Or this is an afternoon time, and we had a good lunch, and now relaxing. Okay, anyway, let me continue. I will move to some more examples now. I'll just show some videos on some of the programs that we are working now to give you some examples on what we discussed so far. So the first video here is a robot taxi, which is a kind of a self-driving vehicle which moves from point A to point B by dynamically adjusting to the environment. Next thing is a kind of a cabin monitoring system where the system automatically observes the driver and passengers and give some suggestions and take decisions accordingly. Basically, it finds the emotions, many aspects. Okay, whether the driver is drowsy, those kind of inferences are made out of the observation. And the third one is a kind of a synthetic scene generation that we use internally to simulate these kind of environments to generate algorithms as well as to verify the same. Let's start with this robot taxi video. Okay, so that gives an idea of how the robot taxi project works. So you can see that okay, the vehicle is utilizing its radar, lidar, and camera inputs to take decisions, to perceive its environment, to take decisions, and its positioning with this perception merged with the HD map, how it takes decisions on the maneuvering. So that is what we demonstrated through this video. So these videos are taken, you can see all these videos in our own YouTube channel, ATAL-FDP YouTube channel. So you can refer to that for more similar videos also. The next video I will show is regarding the cabin monitoring, where you can see how the cabin is monitored and how what kind of decisions are made out of it, what kind of artificial intelligence is applied there. You can see the person is identified here. So it detects that the driver is drowsy and gives some indication. So the viewing angle is calculated. Emotion. If the person is laughing, it is detecting the same. You can see that 3 people are identified separately here, and their emotions are also calculated. Here you can see the static objects like a backpack is identified, and it also gives some indication when the person is moving out without taking that backpack. Okay. So we covered how the vehicle is automatically driving and how the cabin is being monitored. Now, okay, as I mentioned, okay, we'll see how the synthetic scene generation is done to evaluate the performance of different algorithms in different environment conditions. We'll see this video for that. You'll feel that okay, you are playing a game, but this is actually not a game. We are utilizing the same game engines to create an environment. Okay. And each of these vehicles are vehicle models placed in the environment model, and the movement and the behavior is simulated. So the response of the different algorithms, AIML algorithms used in the vehicle in different conditions, when other objects are also behaving in their own way, can be easily identified using putting the vehicle model into this environment model. So we can generate the data sets needs to be used by the algorithms also from this environment to train different algorithms. Can see that we can configure each of these components, okay, each of the environment, different other components, the numbers, their behavior, everything can be configured using the configuration of tools. Okay, I think with that I can stop my presentation here, and if there are any questions, I can address the same. So I'm done with my presentation. So any questions?
Dear participants, do you have any doubts? Please unmute your mic and ask, or you can post your query in the chat.
And you can search YouTube to find many similar applications, okay, in automotive industries, many different cases. So I can explain you what ATAL-X is doing, but there are similar research happening in every other automotive related companies also. Everybody is working on new age technologies now to bring those technologies into the vehicles to improve the experience. So any questions if you have related to this, you can ask me, or you can even post your questions, and we can see.
Sir, I think there is no more queries from the participant side. So can we wind up the session?
Yes, I think we can wind up the session in that sense because I'm done with my presentation.
Okay, sir. Thank you very much, sir, for accepting our invitation as and join with us as a resource person. And now I invite our FDP coordinator, Dr. Anil AR, sir, for delivering the vote of thanks.
Okay. Dr. Ragesh Nge present the mathematical models that are needed in real-time situations, and he explained a detailed presentation related to automated vehicle area. And I hope that everybody understands how these models, machine learning model, there are different types of models are available. All these models are where it is implemented, how it is, what exactly the complexity of converting this model into actual scenario. Uh, Thank you, Dr. Rakesh sir, for his excellent presentation, and thanks to the entire participant for their kind attention for listening this presentation. Thank you, each and every person. Thank you, one and all.
You're welcome, Dr. Anil. And all participants, okay, you can reach me anytime through this forum if you have anything to discuss on these kind of aspects. Okay.
Rakesh sir, you put your email ID in the chat box. That is better.
Yeah, I can give that. Thank you. I have added my email ID to the chat window, so you can see that and you can ask. You can connect with me if I can. If you think I can support you in any way.
Dear participants, there is an important announcement regarding our FDP. We have already intimated you through our confirmation mail regarding AICT adult policy about attendance and assignment. As you all know, AICT is issuing the certificate for all the participants, and as per their policy, the digital certificate will be issued to the participants with the following criteria. They are: participants need attendance more than 80 percentage. Participants need to secure more than 60 percentage marks in the final assessment. We have prepared a quiz for the assessment. And finally, you have to fill up the feedback form on the adult portal at the end of the program. You have to meet these three criteria in order to receive the digital certificate. Once again, attendance more than 80 percentage, marks more than 60 percentage in the multiple choice quiz, and you have to fill up the feedback form on the AICT portal at the end of our program. And regarding the assessment, we will be posting a multiple choice quiz soon after the validity function on tomorrow, and we will share the link through the Meet and also through the WhatsApp group. The quiz will be enabled for 24 hours till Saturday 3:30 p.m. So you can attend at your convenient time. And while entering the feedback on the AICT portal, please ensure that the details provided by you is correct. Once the digital certificate is issued by AICT, correction is not possible. So please check your information. And our tomorrow's session will begins at 9 a.m. All of you may please join sharp at 9 a.m. Thank you all. Thank you, Rakesh sir.
Okay, thank you. Thank you all. Bye. Have a nice
Thank you,
day.
Rakesh.
Yeah. Bye.
Sir, tomorrow
Thank
we
you,
are
sir.
starting early.
Saturday.
Hello, sir. Tomorrow we are starting early.
Tell. No, no,
Sorry, ma'am.
no.
Sorry. Our time is at 9:30. 9:30.
Okay, fine. Thank you.
9:30 a.m. Sorry for that. 9:30 a.m.
And the quiz will be conducted after the validatory.
Yes, ma'am. The link will
Yes,
be
yes,
posted
yes.
after the validatory 3:30 p.m. and it will be enabled for 24 hours.
Yeah, fine. Okay. Thank you.
Okay.
Okay, thank you all. Thank you.